All right, we have two wheels with their masses located in the tire. So all the mass is located around the outside of these things. Spokes contribute nothing. Each have a mass of 1 kilogram, starts from rest, and the forces are applied as shown. In order to impart identical angular acceleration, how much should F2 be? Well, I know that this is kind of a unique problem. I have a hoop spinning around a rotational axis. My rotational axis is at the center, and I want to figure out how to get the same angular acceleration. So I know that I have Newton's second law for rotation, which says my net torque is going to give rise to an angular acceleration. And this is going to be the same in both cases. My net torque 2, my net torque 1, moment of inertia 1, moment of inertia 2. So my net torque 2 is going to give me a moment of inertia 2 times my angular acceleration. So this net torque is going to cause this thing to rotate. They want to have identical angular accelerations, so I'm going to say that they have identical alphas. And I know that their torque is defined as, a simple case of this one is force times the distance it's away times the sine of the angle between the two. Sine of the angle between the force and the distance vectors. Well, my distance vector points up in both cases. My force vector points horizontal, so my angle is going to be equal to 90 degrees, or my sine of the angle is 1. So torque 1 is F1 d1, and that's going to be equal to moment of inertia 1 times alpha. Torque 2, my net torque on this one, I have one force at one distance, so I have F2 d2 is equal to I2 alpha. I'm not done yet because I don't know what Li is. Well, F2 d2, my I is the mass of the object. We have a mass of 1 kilogram for each one. So the same mass for each of them. And it has a distance of 1 meter. So I call this distance d2, this distance d1. So my R1 is equal to, or my R is equal to d2. So this is a value of d2 squared. And I still have my alpha. This guy over here, F1 d1 is equal to its mass, its distance squared. d1 squared, and it's an alpha again. So in this case, I used a moment of inertia for a hoop. So the moment of inertia of a hoop is mr squared. All the mass is at a radius. There's no coefficient in front. All right. So something interesting happens in these cases. I see that one of my diameters will cancel with one of my diameters. Diameter 2 will cancel with diameter 2. So I get F2 over m d2 is equal to alpha. And F1 over m d1 is equal to alpha. And if they're all the same, they have to be all equal to each other. So if my distance increases, if this distance is large, this distance over here is actually large, it's twice as large. In order to get the same alpha, if this is twice as large, the force 2 has to be twice as large. So force 1 was 1 Newton, force 2 is equal to 2 force 1. So 2 newtons. It's a ratio problem. This is not a standard way to solve them, but I solve both cases. I can work out the rest of the math. I just ran out of the room on the page. But I can substitute in that d1 is a factor of, or d2 is twice d1. So I could substitute those in, cancel my terms using these two guys, and find this equation. So it's really interesting. As we increase this radius, not only are we changing the moment of inertia, all this mass is now at a different location, so moment of inertia change, but we're also changing the force, where it attaches to. And since the moment of inertia is squared, that's actually the term that wins out in this, or the larger contributing factor. The larger radius, even though we get more torque for our force, it's not enough to make up for the increase of moment of inertia in this problem.